So, what's a formation reaction? Okay, by definition, the energy released or required to form 1 mole of a compound from its constituent elements in their standard states. An example of a formation reaction would be solid magnesium combining with diatomic chlorine gas. Those are 2 elements in their elemental form, forming exactly 1 mole of the ionic compound magnesium chloride. Do you think this reaction would be endothermic or exothermic? Yeah. So how about I tell you the enthalpy change for the process is negative 641 kilojoules per mole. Now, are you convinced it's exothermic?
Yes.
Yeah. Okay, you can look in the appendix of your book for the thermodynamic values, but usually formation reactions are exothermic, but not always. And if the element is already in its elemental form, its delta HF is 0. And we put a little knot there to show that this only applies at under standard conditions, usually 25 degrees Celsius and 1 atmosphere of pressure. Okay, what's bond enthalpy? We just went over this today. Right. And do you think this should be endothermic or exothermic? Right. Okay, an example would be for diatomic chlorine gas. If we break that bond, we're going to end up with 2 gaseous atoms of chlorine. And the enthalpy for that reaction is going to be positive. It's going to be 244 kilojoules per mole. What is ionization energy?
The energy required to remove an electron.
By definition, this has to occur in the gaseous state. So the states of matter become important, actually. Do you think this one would be endothermic or exothermic? Okay, so let's write an example for the reaction. And this is called IE1, the first ionization energy. That's the energy to remove the first or the outermost electron. So for magnesium, in the gaseous state, we're going to remove 1 electron to form the magnesium plus 1 ion. If we were talking about the second ionization energy, that would be the magnesium cation in the gas phase already, losing a second electron. And we think of this happening in a stepwise process, even though it may not actually occur in steps like that. So the first IE1 has a delta H value 738. What do you think about the second one? Should it be greater than or less than that?
Greater.
Yeah, they get larger, successively larger. So the second ionization is 1,450 kilojoules per mole. Okay, what is electron affinity?
The energy required to gain an electron. The gaseous.
Right, so just the way that I've written it might give you a clue as to whether this is usually endothermic or exothermic, because instead of saying the energy required, I wrote the stability gained. So for some, I'll just say, for some elements, there's a gain in stability. Like, for example, we're going to talk about chlorine. For chlorine in the gaseous state, to gain 1 electron, it's going to form the chloride ion in the gaseous state. That's going to be a stability gain of 349 kilojoules per mole. But for things like the noble gases, they already have a full shell. They do not get a stability gain, and they would actually have a positive electron affinity. We usually abbreviate with EA, like that. So sometimes exothermic, or maybe we could say usually exothermic, unless you're disrupting one of those special cases of stability that we talked about, a half-full subshell, a full subshell, or a full shell. In those cases, it's not exothermic. It's endothermic, actually. But your book doesn't give any of those values if it's endothermic. It just says is greater than 0. Okay, next thing that you need to know to deal with the Born-Haber cycle is atomization energy, and this is something we haven't dealt with really yet, but we are going to get to it actually, changes of state. So what this really is like when you're going from solid directly to a gas. Think of separating the substance from like being close together, like it would be in the solid or the liquid phase, and spreading it out, so that each atom is just alone from the other atoms. Or that's why it's called atomization energy. Or sometimes it's called vaporization. And again, that's for 1 mole per mole. Here would be an example that we're going to need for our Born-Haber cycle. Solid magnesium metal being atomized. So that means it's going to individual atoms in the gas phase. They're no longer near each other. And do you think that this should be endothermic or exothermic? Yeah, definitely endothermic. So this requires energy to get this to happen. So that for this particular example is 147 kilojoules per mole is the energy required to break apart the metallic bonds in the magnesium. Okay, and that brings us to lattice enthalpy. That's the section that we skipped. And lattice enthalpy is usually released in the form of heat, but it's the energy released when 1 mole of a salt or an ionic compound forms from gaseous ions. Seems weird that it would be from gaseous ions. That's probably not how it actually happens, but that's just how we think of it for convenience sake. So an example reaction of that happening would be magnesium 2+ ion in the gas phase coming together with 2 chloride ions in the gas phase and forming exactly 1 mole of magnesium chloride. And do you think this would be endothermic or exothermic? Probably exothermic because of the way I wrote it, like energy released, duh. But we this is the value that now we're going to use the Born-Haber cycle to calculate. Ready? I'm going to draw one for you. with a Born-Haber cycle, I usually put the ionic compound at the very bottom, the lowest in energy. Then the next reaction that I add to the drawing is the formation reaction. So we already wrote the formation reaction. That was magnesium in its metallic solid phase and chlorine diatomic gas. Those are the elements in their standard state. And we said that that reaction was exothermic. So we're going to draw the arrow going down because it's a stability gain and the excess energy will be released.
Magnesium is a solid?
Magnesium metal, you know. Have you ever burned?
Well, I mean, I'm saying because you said in lattice energy that it had to be a gas.
Okay, this is the enthalpy of formation. That's the formation reaction. That's forming 1 mole of the substance from its elements in their standard states. Yeah, pure elements. Okay, good. So that's the first thing I usually put on my diagram. Yeah, and this thing that we're doing is called a Born-Haber cycle. Then you can do this in any order that you want to. I'm just showing you how I do it. It's good to just deal with everything in turn. We're going to have to use all the reactions that we just went over. You have to use all of them, actually. So you can start with whichever one you like. Sometimes I just work left to right. So just because I wrote the metal on the left, let's start with that one. It has to go from a solid and into its atoms, like gaseous atoms. So we are going to write now magnesium as a gas and leave the chlorine the way it was. That's diatomic chlorine gas there. So which of the reactions that we just wrote does that represent? A magnesium solid going to a gas? No. Atomization energy, yes. That is just going from a solid to a gas. Okay. Then I'm gonna keep on dealing with the magnesium. I'm gonna make the magnesium a gaseous ion now. So I'm gonna go from magnesium in the gas phase to magnesium +1 in the gas phase. So which reaction was that?
First ionization energy.
Right, that's IE1 for magnesium. Now I'm going to form the magnesium 2+ ion, and still leave the chlorine alone. And what reaction was that? Yep, the second ionization energy for magnesium. And then the next thing I'm going to put onto the drawing is the bond energy or bond enthalpy. And the reason why I'm doing it in this order is because I'm using up, first I put the formation reaction. I don't know, I'm just in the habit of doing that first. Then I put all of the endothermic processes. So I'm going up to the highest energy state, kind of like getting everything ready. Then when I get to the exothermic processes, I put them on the other side. Okay, so it's kind of like a, well, it's called a cycle, right? Because you can go up and then, like rainfall. Evaporation, condensation, rainfall, and so on. So it has to go like that in a cycle. All right, so the next thing I've already said I'm going to use, I'm going to leave the magnesium 2+ in the gas phase alone because that's already in the form that I want it to be in. But now I'm going to break the bond between the 2 chlorine atoms. So now I have 2 individual atoms of chlorine in the gas phase. And that was my bond energy for chlorine. Then usually I will rewrite everything before I start coming down the other side. Okay, the next reaction that I'm going to use is, well, there's only 2 that we haven't used yet. So the first one that I'm going to use is the electron affinity because I can't form the ionic compound unless the two things are both ions. Right now, magnesium's an ion, but chlorine is not. So I'm going to, again, leave the magnesium alone, and I'm going to need 2 chloride ions in the gas phase, and that was the electron affinity for chlorine. But because the electron affinity is just for 1 mole of an element going to an ion, because there's 2 chlorines here, I'm going to have to take that electron affinity times 2. Yeah? Sort of? Okay. Now, what I have on the slide is, lastly, the lattice enthalpy. So that's my Born-Haber cycle, and the question was asking, like, what is the lattice enthalpy? So in a way, that's asking, like, how long is this arrow, the blue arrow that I've drawn here? And I can actually find that out by determining the length of this arrow in the middle, and then subtracting that arrow there on the right-hand side. So when you're using a Born-Haber cycle, you can have any piece of information missing. And all the other information has to be given to you. So what was the bond energy? It was 244. What was the second ionization energy? It was 1450. The first ionization energy was 738. And the atomization energy was 147. And the formation reaction was 641. And you'll notice that the arrow is kind of showing whether the reaction is releasing energy or requiring energy. So what I've written here are just the absolute values. Okay, because what I'm interested in is what is the length of this arrow. So it doesn't really matter if they're positive or negative. And then the electron affinity, we have to use that twice. And the value, even though it is exothermic, I'm just going to write a 349 here, because I'm just interested in what is the length of this arrow, basically. And then if you sum up all the values on the left and subtract this 2 times the electron affinity, you would find the length of the missing piece of information. And you can do that for anything that's missing. Okay. Now, if you have patience, I mean, you can convince yourself that you could also use Hess's Law. By summing up reactions. Okay, so if you don't like the way that I just shown you by the Born-Haber cycle, if that doesn't help you in any way, shape, or form, you could use the Hess's Law in the way that we've been doing it before. But in order to do that, you need to know how to write the reactions. So our goal is the lattice enthalpy. The stuff that we know, remember Hess's Law? Like for me, I like to just kind of put stuff in there to line it up with where I'm trying to get to. Oh, line up my arrows. You want to line up your arrows too? Where was the Mg2 plus gas? It was in the second ionization energy. But I flipped it around, see? So that's the first ionization energy written backwards. So if it was before requiring 1450 kilojoules, now it's releasing 1450 kilojoules. Okay, now I have an Mg plus, which does not appear in the goal reaction, so I have to get rid of that. So I'm going to put the Mg plus And you can see here the states of matter. Okay, so the value for that was 738, but I flipped it around, so now it's exothermic. Okay, what do we have now in the reaction that we don't need? Mg gas. Okay, so we're gonna use the reverse of the atomization energy. So the atomization energy was 147. Now it's negative 147. Okay, now I have an Mg solid in there that I don't need. So I have to put Mg solid on the other side. What reaction had Mg solid in it? What reaction is that? That's the formation reaction. And the enthalpy of formation was the same as it's written now, same direction, 641 kilojoules. But it was negative, and I didn't flip it, so it's still how it was. Okay, now we have the MgCl2, we want that. We have the Mg2+, we want that. But we still have a Cl2 gas that we don't want, and we don't have Cl2Cl- gaseous ions yet in there. So we got to get rid of this Cl2 gas. So the reaction that we had Cl2 gas in was the bond enthalpy. Remember that? So we got to break that bond. And this is written as going to be exothermic. No, 244. Okay, and last but not least, we have to electron affinity. Yay! But we have to use that twice still, right? Because we have 2 chlorine. We got to get rid of those, so we put those on the other side. And what we want to have in there are 2 chloride ions in the gaseous phase. And so that's going to be 2 times, now, oh, I don't really have room for it, but there's also 2 electrons here that are going to cancel out with these 2 electrons over here. So that's going to be 2 times a positive 349, because I had to flip it backwards from the way we had written it before. So, by this method, we should come up with the same number as the other method. And just in case you don't believe me, we can cross out everything now. 2 electrons, magnesium plus, magnesium gas, magnesium solid, chlorine diatomic, chlorine that's not an ion, and we're only left with the things that appear in our goal reaction. Right? Okay, so you're all experts in either using a Born-Haber cycle, or if you don't like that, you can always do it this way. But you still have to find the unknown value. If you do it this way, you have to know how to write the reactions for ionization energy, atomization energy, formation reaction, bond energy, and electron affinity and lattice enthalpy. You have to know the definitions in order to write the reactions correctly. So anyways, finish the rest of the thing. You have 10 minutes. Just do your best.